Hey team, better late than never. This is video 17. You can see my notes up in the left side of your screen. I'm also going to put a PDF of those notes under lecture notes, and in particular under video lecture notes. So don't feel like you have to scramble to write this stuff down. Video 17 is about the difference between statistical significance and substantive significance. In particular, we want to figure out what does it actually mean to say that something is statistically significant. The way to start explaining is to say that statistical significance is always set against a backdrop of the real answer is 0, or the real difference is 0, or the real effect is no effect. So that will be our null hypothesis. We'll talk about null hypotheses a little bit more in the next video. But again, the backdrop is if the real population result were 0 or no difference, how likely would it be to draw a sample with a result this extreme by chance? And that likelihood, that probability, is the p-value. And in particular, it's the p-value that you get when you run a t-test or a linear regression. Again, that's the probability that a result or a difference this extreme would happen by chance, by selecting a random sample. In some sense, the p-value is kind of an inverse of a confidence interval. They both rely on the central limit theorem and its finding that roughly 95% of all sample means will be within 2 standard errors of the true population mean. And so from the central limit theorem, we get confidence intervals, and we also get the sort of idea of a p-value. So in a couple of weeks, when we talk about linear regression, that's one way to talk about the p-values that appear in linear regression output. The thing I'll say about it, though, is that it can be a little confusing if what you really want is just a confidence interval. If you just want a confidence interval and you use the t-test function for that, you're going to see a p-value that's absurd. 2 to the -16th or something bonkers like that. And the reason for that is, well, you really want the confidence interval. You don't care in particular, unless you think the true mean is 0, unless you have reason to believe that, you don't really care whether the true mean is 0. You just kind of want to know what the confidence interval around your sample mean is. In any case, so that's a reason when you look at a one sample t-test to kind of ignore the p-value and move on to and just look at the confidence interval. So I want to just sort of go through a t-test example. You don't need to reproduce any of this code. These are all examples that we are just going to sort of check through. So the first thing I've done, looking in the console, is a one sample t-test. That's what you should have done in your homework. And the data is x3. So x3 up here is a sample of size 100. So 100 random numbers taken from a normal distribution with a mean of 50 and a standard deviation of 15. So it's kind of a wide-ish curve. And what we see here is, right, the p-value is less than 2.2 times 10 to the -16th, so the p-value is effectively 0. So we would then accept the alternative hypothesis that the true mean isn't equal to 0, but we don't care about that so much. What we want to see is the 95% confidence interval, and that is from 48.71715 to 54.367. And that is indeed, right? So the mean of X is 50. The mean of this sample is about 51.5. The confidence interval 48.7 to 54 point roughly 4. And indeed right, there's X3, 50, the mean of the distribution from which x3 is drawn, is in our 95% confidence interval. Woohoo! So that's a one sample t-test. We've done that before. We use that to get a confidence interval in many cases. The next thing is to consider a two-sample t-test. We're going to do that in more detail in the next video. Another way of thinking about p-values is that it's a way of taking sort of variation or spread into account when you assess the difference between two distributions. And so the key point here is that the same size difference can be significant or not significant depending on the level of variation in your two samples. So take a look at this pretty picture I made you. Here it is. I'm going to move myself over here. Hey, there I am. What I've done here, this is a little confusing to look at, but what it is a set of 4 samples. 4 samples, all drawn from random normal distributions, and they all have, there are 2 samples in black and 2 samples in red. So samples in black are these curves, and their means are shown with the dotted lines. The samples in red are shown with these curves, and their means are shown with red lines. The key point here is that we find that there's a significant difference between the two. They all have the this black distribution and this red distribution have the same mean. Same with this rightward black distribution and this rightward red distribution. So the ones on the left and the ones on the right have the same distribution, or have the same means, excuse me. What's different is the spread. So the black distributions, as you can see, are much narrower, the red distributions are much wider, and consequently, we find, so moving back over here to the console, here is a 2-sample t-test. So we do that by, since these are independent samples, we do that with a comma. That's actually going to be rare in our analysis. So we print a t-test x1, x2, those are the black ones, and we find that the 95% confidence interval is from -5.38 to -4.84, and guess what? That is a highly significant difference. On the other hand, as you won't be surprised to hear, that despite the fact that the actual difference between the means for the 2 red samples is just the same as the difference in the means of the black samples, the t-test is not significant. You can tell it's not significant because the p-value is 0.38, 0.39, and we typically only reject the null when the p is less than 0.05. In addition, and possibly more usefully, you can see that the confidence interval crosses 0. So if the confidence interval goes from -6 to 2, that means that 0, that is to say no difference between those distributions, is within our confidence interval. And so we do not reject the null hypothesis. So that is our second example. And the one thing I want to add at the sort of end here is to say that statistical significance is not the same as substantive significance. It's statistical significance. You can have huge statistical significance with very little substantive significance. If you had a huge sample, for example, or if your sample had very little variation in it. So the less variation and the larger the sample, the likelier you are to end up with a significant difference. All right, I'm going to say more about all of this stuff in the next video, so stay tuned.